So here we're going to have the ambiguous case of angle side side. So let's set this up as we did before with law of sines. So we're going to have a side length here. Let's see, I'm going to estimate 35 degrees, which is maybe something like this. Let's see, this will be 8, which is kind of long. Let's say something like that. All right. Now, first off, we need to figure out, let's fill in these angle measurements. So this is going to be beta of 35 degrees. Then we'll have A, which is 8. And then we're going to have B, which is 6, but I'm not going to draw it yet since this is the angle side side, and I'm not sure what my triangle looks like yet. So what we need to do is figure out how many solutions are we going to have? Is it going to be 0? So that's the case where when we look at this side length of 6, it's too short, like it doesn't hit the bottom of the triangle. Is there one solution, like one right triangle, where that 6 is equal to the height? Are there going to be 2 solutions, which is where 6 is longer than the height, but shorter than 8, so that when we kind of swing that around, we end up with 2 spots that we could land at? Or, which actually we can already throw this one out, the other case is one triangle, and that's where this value over here for this other side length would be longer than 8. So if that was the case, then we would just have one triangle with where that would land over there. But we can throw out that one. So what I need to do is I need to look at the height of this triangle. So just to get an idea of what that value is. So with that, I would take sine of 35 degrees is opposite over hypotenuse. So h is equal to 8 times sine of 35 degrees. And plugging that into a calculator, that's a 4.59. So what that tells me is that I want to have this length of 6. So if this is 4.59, 6 is longer, but it's shorter than 8. So this is the case where we're going to have 2 triangles come through. So what I could draw is something like this. Either it's going inside of here or going outside of there. And that would be my side length of 6 and my 2 possibilities for beta as well as gamma. Okay, so this is the case where we have 2 triangles. And what we'll go ahead and do is split up our possibilities here. So I'm going to go ahead and draw kind of the larger and the smaller. Something like that. All right. Now I'm just going to fill in what I know. 8, 8. And then we're going to have alpha is unknown, gamma is unknown, C is unknown. Now, with last week, we had law of sines. We could start plugging in. We do have this pairing of an angle measurement and side length. However, and if it just said solve each of the following triangles, like if this was the setup, then it's technically your choice. But what I want to emphasize here is that sometimes it might specify. So if it said solve each of the following triangles using law of cosines, this is what I want to show here is how do we specifically use law of cosines here. So what I can use is that we have this angle measurement, we have this side length. So let's say I wanted to find this missing side length here. So what I can do is set up law of cosines around 35 degrees. So what that would mean is I'm building it around beta. So what that would do is put b squared on one side of the equation and then equals a squared plus c squared minus 2ac times cosine of beta. Filling in the numbers that we know, I would have 6 squared equals a squared, which is 8. C is unknown. 2 times 8 times c times cosine of beta, which is 35 degrees. And I'm just going to simplify. So here's a 36. Here's a 64. I still have this unknown c squared. I have 2 times 8, which is 16. What I'm also going to do is just in a calculator, cosine of 35. So I'm taking 2 times 8 times cosine of 35, which is about 13.11. And then that's multiplying with c. So what we end up with here is a quadratic. We have c squared, we have just c, and then I have these constants. So what I want to do is get 0 on one side of the equation to solve this. So I'm going to subtract 36 from both sides. So I'm going to have c squared minus 13.11c, and then 64 minus 36, which is 28. Now, this isn't going to factor easily, but what I can use is the quadratic formula. So quadratic formula, a equals 1, b equals negative 13.11, c equals 28. And solving for c, we'll get negative b plus or minus square root of b squared minus 4 times a times c, all over 2 times a. And with this, we're going to get 2 solutions. So we can just use the calculator for this. And in fact, let me jump over to a calculator. So we can plug this into the calculator. So I'm going to split this up. We're going to have 13.11. And negative will make a positive. Let's go ahead with addition here. And square root of negative, we could use parentheses there, negative 13.11 squared. And then minus 4 times a times c, all over 2 times a. And we get 10.423. I'll just do 10.42. So there's one solution. The other solution comes from having subtraction. So then what I'll do is just edit this, take out that addition, put in subtraction, 2.69. So with this work, you might be like, wow, this is so much more work than law of sines, and we had to use quadratics and the quadratic formula. But the nice part of it is that you actually end up with 2 solutions here. This starts solving your triangles. So this is giving you 2 possibilities for c, which comes through in our pictures up here. So that 10.49 is this case where we would have a longer value of c, and the 2.69 is coming through over here with that shorter side length. So with that, we end up with 2 solutions, basically 2 side lengths to our triangles in kind of one round of work there. So now we need to find our angle measurements. So to do that, what we're going to do is we need to switch over to law of sines. We could try to use law of cosines, but that gets a bit tricky with these 2 separate triangles. So we just want to use law of sines, and using the fact that we used before that what we'll do is we'll be finding this value for alpha just by how inverse sine works. And then we can find the second alpha using 180 minus that one that we're going to solve for right now. So I have sine of 35 degrees to 6 is equal to sine of alpha to 8. And then what I'm going to do is just solve for sine of alpha, and then I'll even take inverse sine of both sides. So it's that we're taking inverse sine, and if we had multiplied both sides by 8 sine of 35 degrees over 6. So to get alpha, we'll have inverse sine, 8 sine of 35 over 6, which is 49.89 degrees. And then for gamma, so if I fill that in, 49.89 degrees. And then solving for gamma, just 180 minus 35 minus 49.89, and that would be 95.11 degrees. All right. Then to find alpha over here, we're just taking 180 minus that 49.89, since those are supplementary to each other. So 180 minus 49.89. So that would give us 130.11 degrees. And then for gamma, 180 minus 35 minus 130.11. And that's 14.89 degrees. So with that, we can start using law of sines. So even if it says specifically to use law of cosines, that's really talking about the beginning of the problem. We could use law of cosines here to find the angle measurements. It just gets really tricky and you'd want to be very careful with your two separate triangles. But where we practice law of sines, you could just use that there.